Good evening, thoughtful traveler, and welcome to this quiet corner of the night. Whether you're here to gently close your day or to let your mind drift through the stillness of space and thought, I'm grateful you've arrived. Tonight, we won't hurry through formulas or breakneck discoveries. Instead, we'll float calmly into the vast, elegant silence of the cosmos. If you'd like, feel free to share in the comments where in the world you're listening from. There's something quietly beautiful about knowing that across cities and continents, strangers become companions in curiosity. And if the deep rhythm of the universe, its distant galaxies, strange particles, and timeless questions speaks to something in you, I invite you to subscribe. There are so many more serene journeys ahead. Now, let us begin. Chapter 1: The Birth of the Universe. Roughly 13.8 billion years ago, what we now call the universe emerged from an event we refer to as the Big Bang. The name itself is misleading. It wasn't an explosion in space, but rather an expansion of space itself. In an instant, what had been a single, unimaginably dense point, a singularity, began to grow. And with it, time, space, and the potential for all that would ever exist unfolded. This moment wasn't marked by sound or light. There was no air to carry vibration, no sun to shine. It was a birth not of noise, but of possibility. At first, the universe was a seething, incomprehensibly hot plasma of energy and fundamental particles. Quarks and gluons, the tiny, restless ingredients of matter, danced in wild, chaotic motion. The four fundamental forces that shape reality today: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have once been unified in this high-energy state, indistinguishable from one another. But as the universe cooled, they began to separate, like colors appearing as light refracts through a prism. It would remain this way for nearly 380,000 years. This era is often called the Cosmic Dark Age, not because it was absent of activity, but because it was invisible to light. Still, the universe expanded, and as it did, it cooled. Slowly, the wild particles began to calm. Temperatures fell to a point where electrons could finally join with nuclei, forming neutral atoms. This was a moment of transformation and transparency. With electrons now bound into atoms, photons, particles of light, were free to travel. This release of light is known as recombination, and the afterglow of this moment still fills the universe today. It is called the cosmic microwave background, or CMB, a faint radiation that reaches us from all directions, a ghostly echo of the universe's first light. To study the CMB is to look back in time, across billions of years, to glimpse the universe as an infant. Slight temperature differences in this background radiation, just a few millionths of a degree, reveal the earliest imprints of structure, tiny fluctuations in density that would, over time, grow into galaxies, stars, planets, and all the complexity we now observe. But the journey from a smooth glowing mist to a structured universe was long. Gravity, the weakest of the four forces but infinite in its reach, played the leading role. It gently tugged at those tiny variations in density, causing matter to collect in certain regions more than others. Over millions of years, clouds of hydrogen and helium began to gather, slowly collapsing under their own weight. Where enough mass accumulated, temperatures and pressures grew high enough for nuclear fusion to ignite, and with it, the first stars were born. These first stars were massive, hot, and short-lived. They burned bright and died young, many in spectacular supernova explosions. In their cores and in their deaths, they forged heavier elements: carbon, oxygen, iron, the building blocks of life as we know it. These elements were scattered into space, seeding the next generations of stars, forming the material for planets, oceans, and eventually sentient beings capable of asking where it all began. The formation of the first stars marked the end of the cosmic dark ages and the beginning of a new era, one filled with light, structure, and change. Galaxies began to form, swirling islands of stars bound by gravity. Our own galaxy, the Milky Way, took shape during this time, though it would be billions of years before our solar system would emerge. And still, the universe expanded. It's important to note that this expansion is not like an explosion flinging debris outward into empty space. Instead, space itself is stretching, carrying galaxies with it. On vast scales, this expansion means that distant galaxies are moving away from us and from each other, not because they are traveling through space, but because space itself is growing between them. This idea, counterintuitive though it may be, is supported by observations. The light from distant galaxies is redshifted, stretched into longer wavelengths as it travels through expanding space. The more distant the galaxy, the more redshifted its light, and the farther back in time we are seeing. Through this lens, astronomers have peered deep into the past, uncovering a timeline of cosmic evolution that continues to unfold. There is, of course, much we still do not understand. What caused the Big Bang? What, if anything, came before it? What is the nature of the dark matter that outweighs visible matter yet cannot be seen? And what is dark energy, the mysterious force driving the universe's expansion to accelerate? These questions lie at the edge of human knowledge, and perhaps always will. But in seeking their answers, we discover not only facts about the cosmos, but perspectives on ourselves. We learn that we are made of ancient stardust, shaped by forces that trace back to the first moments of creation. We find that our place in the universe is not central, but it is meaningful, simply because we are capable of contemplating the whole. The birth of the universe is not just a tale of particles and physics. It is the origin story of every question, every thought, every being that ever was. And as we listen closely to those first, distant whispers from the beginning, we are reminded of something quietly profound, that even the vastest silence contains the promise of light. Chapter 2: Silent Laws. Gravity, light, and the shape of everything. As the universe continued its slow unfolding from that brilliant origin, something remarkable became clear. The chaos of energy and matter did not spiral into randomness. Instead, it organized itself according to quiet, unwavering principles. Invisible forces gave shape to everything we now see, from the spin of a galaxy to the path of a falling leaf. Among these principles, gravity stands as one of the most mysterious and persistent. It has no voice, no color, no form, and yet it moves stars, bends light, and shapes time. Gravity is the force that keeps planets in orbit, gathers dust into stars, and holds galaxies together across unimaginable distances. And still, it is the weakest of the four known forces of nature, far weaker than the electromagnetic force that causes a magnet to cling to metal, far more subtle than the nuclear forces that bind atoms. But what it lacks in strength, it makes up for in reach. Gravity never fades to zero. Its influence stretches across the universe. Long ago, Isaac Newton described gravity as an invisible pull between masses, a kind of tether drawing objects together. But centuries later, Albert Einstein would transform this idea forever. He showed that gravity is not a force in the traditional sense, but a bending of space and time caused by mass and energy. The more massive an object, the more it warps the fabric of the universe around it. Imagine placing a heavy ball on a stretched sheet of fabric. The ball creates a dip, and anything nearby naturally rolls toward it. This is how gravity works, not by pulling, but by curving the space that everything moves through. The Earth doesn't orbit the Sun because it is being tugged. It moves along a curved path in the warped space-time around the Sun. Even light follows this curve. Einstein's theory of general relativity, proposed in the early 20th century, predicted many strange and beautiful things. That time would move more slowly in strong gravitational fields, that massive objects would bend the paths of starlight, and that ripples in space-time, gravitational waves, could travel across the cosmos like echoes from distant events. And each of these predictions has since been observed. In 2015, a century after Einstein's theory was published, gravitational waves were detected for the first time. Two black holes had collided over 1 billion light-years away, and the ripple they caused stretched space itself, just enough to be measured on Earth. By instruments so sensitive, they could detect a movement smaller than the width of a proton. That ripple was not sound, it was not light, it was the universe itself, shivering ever so slightly, a reminder that space is not static, but supple, not silent, but resonant. But gravity is only one of the silent architects of reality. Light, or more precisely, electromagnetic radiation, plays a different but equally essential role. Light is both a particle and a wave, a dual identity that puzzled physicists for generations. It travels at a constant speed, nearly 300,000 kilometers per second in a vacuum. This speed is not merely fast, it is fundamental. Nothing can move faster. It is the ultimate speed limit of the universe. Because of this, light becomes a kind of time machine. It carries information from the past. When you look at the moon, you see it as it was about 1.25 seconds ago. The sun appears as it was over 8 minutes in the past. And distant galaxies, their light stretched into infrared and microwave signals, show us what the universe looked like billions of years ago. This stretching of light is known as redshift. As space expands, the waves of light traveling through it are stretched too, shifting toward the red end of the spectrum. The farther away a galaxy is, the more its light is redshifted, and the older its story. In this way, light becomes both messenger and memory. But space itself is not merely the stage where objects move. It has shape, curvature, and even energy. When we speak of the shape of the universe, we are not describing something like a ball or a cube. We are describing geometry on a cosmic scale. Is the universe flat, curved like a sphere, or open like a saddle? Observations of the cosmic microwave background, the afterglow of the early universe, suggest that space is remarkably flat. Parallel lines, if extended forever, would remain parallel. And yet even this subtle flatness exists within a universe that continues to stretch. This expansion is not like an explosion. It does not hurl matter into empty space. Instead, it stretches space itself, like ink expanding on a balloon. And as space stretches, galaxies drift apart. Not because they are moving through space, but because the space between them is growing. Even more surprising is that this expansion is accelerating. In the late 1990s, astronomers studying distant supernovae made a discovery that changed everything. The universe is not just expanding, it is doing so faster and faster over time. Some unknown energy, now called dark energy, is pushing space apart. Dark energy does not glow. It cannot be touched or weighed, and yet it seems to make up about 70% of the total energy in the universe. Its nature is still a mystery, but its effects are measurable. If it continues unchecked, distant galaxies will eventually slip beyond our view, their light stretched so far that it can never reach us. This expanding emptiness leads to profound questions. What is the ultimate fate of the cosmos? Will it continue to stretch forever, cooling into silence? Will it slow, stop, and collapse into a new singularity? Or will it reach some unknown state we have yet to imagine? These questions are not just theoretical. They speak to the nature of the laws that govern us, the laws that guide the dance of atoms, the path of light, the shape of time. They are not laws in the human sense, written by authority or decided by vote. They are patterns, revealed through observation, mathematics, and the quiet unfolding of the cosmos itself. And as we continue to explore them, we are reminded that we are not separate from these laws. We are made of matter shaped by gravity. We are collections of atoms animated by energy. We are beings whose thoughts are carried on waves of electric charge, bound by the same rules that sculpt galaxies. In learning how the universe moves, we begin to understand how we move within it. Chapter 3: The Quiet Expansion, Dark Energy, and the Growing Cosmos. If gravity is the great gatherer, the force that pulls stars into galaxies and planets into orbits, then dark energy is its quiet opposite. The force that pushes, stretches, and unbinds. Together, these two shape the large-scale story of the cosmos. One draws things together, the other urges them apart. But dark energy is not something we see or feel. We do not experience it in daily life. It has no color, no weight, and leaves no visible trace. And yet, according to our most precise measurements, it makes up nearly 3/4 of everything that exists. The rest is mostly dark matter, and only a small fraction, a few percent, is made of the atoms that form stars, planets, oceans, and us. The discovery of dark energy was not the answer to a long-sought question. It was the unexpected result of looking deeper into the sky than ever before. In the late 1990s, two teams of astronomers set out to measure how fast the universe's expansion was slowing down. Since the Big Bang, space had been stretching, but it was widely assumed that gravity pulling on all matter would gradually bring that expansion to a stop, maybe even reverse it. The question was whether the universe would coast forever or eventually collapse in a kind of cosmic retreat. To find out, they studied distant exploding stars called Type Ia supernovae. These are stellar events so bright they briefly outshine entire galaxies. More importantly, they always shine with nearly the same intrinsic brightness, which makes them reliable markers of distance. Cosmic lighthouses. But when the data came back, something astonishing emerged. These distant supernovae were dimmer than expected, not because of dust nor because of error, but because they were farther away than they should have been. The only explanation, the expansion of the universe, was not slowing down. It was speeding up. This was not a gentle increase. It was a persistent, accelerating push, as if the fabric of space itself was being driven outward by something with negative pressure, a kind of repelling energy. Thus was born the term dark energy, not because we understand it, but because we do not. We do not know if dark energy is a property of space itself, or if it arises from some new and unknown field. We do not know if it will remain constant, increase, or fade. What we do know is that it is deeply woven into the structure of the universe, and that its influence becomes stronger over time. In the early universe, matter and radiation dominated. Galaxies clustered, stars formed, and gravity shaped the visible cosmos. But as space continued to expand, the density of matter thinned, while dark energy, which does not dilute, began to take over. Today, its effects are unmistakable. Distant galaxies are moving away from us faster than ever, and the farther they are, the faster they flee. Imagine a loaf of raisin bread rising in the oven. Each raisin is a galaxy, and the dough is space itself. As the dough expands, the raisins move apart. But in our case, the dough is not just rising, it's accelerating, driven by some unknown ingredient in the recipe of reality. This expansion carries profound consequences for the future. If dark energy continues to act as it does now, the universe will keep expanding faster and faster. Galaxies not gravitationally bound to us will slip beyond our horizon, becoming unreachable. Their light, stretched into ever longer wavelengths, will no longer arrive. Over time, the night sky will grow emptier. The cosmic web of galaxies, vast and intricate, will fade from view. In this future, only the galaxies within our local group, gravitationally tied to the Milky Way, will remain visible. All else will vanish from our observational reach, not because it ceases to exist, but because the light it sends can no longer outpace the growth of space between us. And yet, for all this drift and distance, the expansion of space itself is not something we feel. It is not a wind nor a current. It does not stretch the atoms in our bodies or the walls of our homes. On local scales, within galaxies, solar systems, even between stars, gravity still holds firm. It is only on the largest scales, across tens or hundreds of millions of light years, that dark energy's influence becomes dominant. Still, the fact that the expansion is happening at all, and that it is accelerating, raises questions that cut to the heart of cosmology. Why does the universe have just enough energy to be flat? Why did dark energy begin to dominate only after billions of years had passed? Is it constant, or is it a temporary phase in a larger, more complex evolution? Some theories suggest that dark energy could be linked to the vacuum energy of quantum fields, the so-called energy of empty space. Others propose that it might be part of an undiscovered fifth force, or a sign that general relativity, brilliant as it is incomplete. There are even ideas that the acceleration could reverse, that dark energy might decay, or that it might increase to the point where it tears apart galaxies, stars, and eventually atoms, a theoretical end called the Big Rip. None of these scenarios are certain. Each one depends on the true nature of this unseen force, and we are still very much in the early stages of understanding it. But what is clear is this: the universe is not static. It is not even simply expanding. It is evolving in ways we did not expect, shaped by something we cannot yet name. And in that, there is both mystery and beauty. We live in a cosmos that is moving, stretching, changing, not only in space, but in time. And the more we learn, the more we realize that we are standing on a moving platform, looking outward into a landscape whose boundaries shift with every new discovery. Dark energy reminds us that the universe does not owe us clarity. It offers its truths slowly, with patience, and it is up to us, curious, finite, temporary, to listen as best we can. Chapter 4: The Star's Secret Life. From nebula to supernova. In the stillness between galaxies, in the gentle arms of cosmic clouds, stars are born. They do not arrive with flashes or fanfare. Their beginnings are quiet, almost invisible, hidden within the dark shrouds of interstellar dust and gas. These clouds, called nebulae, are the fertile grounds of creation. Vast, cold, and filled with potential. A nebula may span dozens or even hundreds of light years, drifting slowly through space, shaped by gravity and time. It is in these places that the ingredients for stars gather: hydrogen, helium, and traces of heavier elements, scattered remnants of ancient stellar deaths. For long stretches, nothing happens. Then, something shifts. A ripple, a shockwave from a nearby supernova, a gentle disturbance from the pull of a passing star, and within the cloud, a region begins to collapse. Under its own gravity, the gas compresses. As it falls inward, it heats. What was once cold becomes warm, then hot, then incandescent. The pressure builds. The particles at the center move faster, colliding, fusing. And when conditions are just right, a new light appears. Not from reflection, not from fire, but from fusion. This is the moment a star is born. Fusion is the process at the heart of every star. It is what turns matter into light, what allows mass to become energy. In the cores of stars, hydrogen atoms are pressed together with such force that they overcome their natural repulsion. They merge, forming helium and releasing a burst of energy. That energy pushes outward, creating a balance against gravity's pull. This delicate tension between inward collapse and outward pressure is what allows a star to shine. The young star, called a protostar, slowly stabilizes. Around it, leftover gas and dust may form disks, then planets, then entire solar systems. And for the next several million or even billion years, the star will live in relative peace, fusing hydrogen into helium, radiating heat and light across the void. The length of a star's life depends entirely on its mass. A small star, like a red dwarf, may burn slowly for trillions of years. A medium-sized star, like our Sun, will live for about 10 billion years. The most massive stars, bright and blue and fierce, may live for only a few million years before burning out in a sudden, dramatic end. But all stars, regardless of size, follow a similar path. They are born in clouds, they shine in balance, and eventually they change. As a star runs low on hydrogen, its core begins to contract. The temperature rises. If the star is large enough, helium begins to fuse into carbon. And then, depending on mass, other elements follow. Oxygen, neon, magnesium, silicon. In layers like an onion, each fusion process producing less energy than the one before. At the heart of this process is iron. Iron is the boundary. It cannot release energy through fusion. When a star begins to produce iron in its core, it is near its end. No longer able to resist gravity's pull, the core collapses. In less than a second, it shrinks with unimaginable force, and the outer layers fall inward. Then, an explosion. The core rebounds. A shockwave races outward. The star tears itself apart in a cataclysm known as a supernova. This is not destruction for its own sake. It is the final act of creation. In the fierce heat and pressure of a supernova, elements heavier than iron are forged. Gold, uranium, platinum. The periodic table is completed in these final seconds, and the remnants are hurled into space, enriching the cosmos with the raw materials for future stars, planets, and life. What remains depends on the star's original mass. A smaller, massive star may leave behind a neutron star, a city-sized sphere of neutrons so dense that a teaspoon of its material would weigh more than a mountain. Spinning rapidly, with magnetic fields trillions of times stronger than Earth's, these neutron stars can emit beams of energy like lighthouses. We call these pulsars. If the star was larger still, the collapse continues. Gravity overwhelms all forces. Not even light can escape. A black hole is born, a region of space so curved, so steep, that it becomes a one-way gate. What enters does not return. And so the life of a star, which began in silence, ends with impact, not just on its surroundings, but on the history of the universe. Every element heavier than hydrogen in your body, every atom of calcium in your bones, of iron in your blood, of oxygen in your breath, was once forged in a star. And many of them came from stars that died long before our solar system formed. The story of stars is not separate from our story. It is our origin. We are, quite literally, made of stardust. And even now, new stars are being born, hidden inside quiet clouds, waiting for the moment when gravity, time, and heat align, and a new light appears in the sky. Chapter 5. The Black Hole's Invitation, where matter meets mystery. In the quiet aftermath of a massive star's death, something extraordinary can happen. If the star is heavy enough, far heavier than our Sun, its core continues to collapse beyond all known resistance. Not even the powerful repulsion between atomic nuclei, nor the quantum pressure that supports neutron stars, can hold it back. What emerges is not simply an object, it is a boundary, a place in space where the rules of physics, as we know them, begin to bend. We call it a black hole. The name is fitting but incomplete. A black hole is not just black. It is a region from which nothing, not even light, can escape. And it is not exactly a hole either. It does not lead somewhere. It is a place where matter has been crushed into a point of infinite density, called a singularity, surrounded by a boundary known as the event horizon. Once something crosses this horizon, it cannot return. It is not pulled back, it is sealed in. To approach a black hole is to enter a world where space and time become stretched, curved, and twisted. To an outside observer, time near the event horizon appears to slow, almost to a halt. Light, trying to escape, is pulled back, its wavelength stretched into darkness. The black hole becomes invisible, a shadow surrounded by distorted light. But black holes are not monsters, roaming space at will. They obey the same laws as stars and planets. They form from the collapse of massive stars or through the merging of smaller black holes. They grow by feeding, slowly, steadily, on nearby gas, dust, or the occasional passing star. When a black hole feeds, it creates one of the brightest phenomena in the universe. As matter falls inward, it accelerates and heats, forming a disk around the event horizon. This accretion disk shines with X-rays and high-energy light, often visible across vast cosmic distances. It is one of the few ways we can detect a black hole, by what happens just outside its grasp. At the centers of galaxies, including our own, there are black holes millions or even billions of times more massive than the Sun. These are called supermassive black holes. Their origin remains a mystery. Some may have formed from the merging of smaller black holes, others from massive clouds collapsing directly. But however they came to be, they now sit in the heart of galaxies like silent anchors, shaping the motion of stars and gas on galactic scales. In 2019, scientists captured the first direct image of a black hole's shadow. Using a global network of telescopes called the Event Horizon Telescope, they revealed the outline of the black hole at the center of galaxy M87, a giant more than 6 billion times the mass of our Sun. The image showed a glowing ring surrounding a dark center, just as theory predicted. But despite these triumphs of observation, the interior of a black hole remains hidden. Inside the event horizon, our known laws of physics break down. General relativity predicts a singularity, a point of infinite curvature and density. But quantum mechanics, our theory of the very small, cannot yet describe what happens there. The two great pillars of physics, each stunning in its accuracy, remain ununified in the heart of the black hole. This tension has led to one of the deepest puzzles in modern science, the information paradox. In the 1970s, Physicist Stephen Hawking showed that black holes are not entirely black. Due to quantum effects at the event horizon, they emit a faint radiation, now called Hawking radiation. Over time, this radiation causes black holes to lose mass and eventually to evaporate. But here lies the problem. If the black hole disappears, what happens to the information about everything it consumed? According to quantum mechanics, information cannot be destroyed. But in Hawking's model, it seems to vanish. A violation of a fundamental rule. This paradox has led to decades of debate. Some theories suggest that information is somehow encoded in the Hawking radiation. Others propose that it is preserved on the event horizon, like a hologram. Still others suggest that black holes are not as opaque as they seem, that information may escape in ways we do not yet understand. Whatever the answer, it touches the very foundation of physics. To resolve it would mean finding a unified theory, one that connects gravity and quantum mechanics into a single, coherent picture. For now, black holes remain both real and symbolic. They are places where our understanding ends and where new understanding may begin. They are not voids, but markers, not endings, but invitations. To study a black hole is to stand at the edge of certainty and peer into a realm where time slows, space folds, and the future becomes hidden. They challenge our mathematics, our assumptions, and our imagination, and they remind us that even in the vast openness of the cosmos, there are places where mystery still holds the final word. Chapter 6. Cosmic Clocks. Time, Relativity, and the Universe's Rhythm. Time feels so familiar. A constant rhythm, a silent forward current in which we live our lives. Seconds tick, days pass, seasons change. We measure it with watches, calendars, the aging of faces, and the movement of stars. Yet, for all its familiarity, time is far stranger than it first appears. In the early days of science, time was thought to be absolute, the same for everyone, everywhere. Newton imagined a universal clock ticking in the background, unaffected by speed, position, or circumstance. But in the 20th century, this view was quietly undone. Albert Einstein, through his theories of special and general relativity, revealed something extraordinary. Time is not fixed. It can stretch and shrink. It flows differently depending on how fast you move and how close you are to massive objects. Time, like space, is woven into the fabric of reality. And that fabric bends. The first insight came with special relativity. Imagine two people, one standing still on a platform and one riding a train that moves close to the speed of light. If both hold identical clocks, the person on the train will experience time more slowly than the one on the platform. To the person riding the train, nothing feels different. But to the observer on the platform, The traveler's clock ticks more slowly, their heartbeat slows, even their thoughts take longer. This is not an illusion, it is measurable. The faster you move, the slower your time flows compared to those who remain still. This effect is known as time dilation, and though we do not travel at such extreme speeds in daily life, we do see time dilation at work. Satellites that orbit Earth, especially those used for global positioning, must correct their internal clocks to account for this phenomenon. Without those adjustments, GPS systems would become inaccurate within minutes. Then came the second insight, general relativity, which describes how gravity affects time. Just as mass bends space, it also stretches time. The stronger the gravity, the slower time passes. Near a massive planet, time flows more slowly than it does far from it. Near a black hole, time nearly stops. This too is not just theory. It has been tested and confirmed. If you place two identical atomic clocks at different altitudes, say one at the base of a mountain and the other at its summit, the one lower down, closer to the center of Earth's gravity, will tick more slowly. The difference is tiny, but real. These effects accumulate over distance and time. Astronauts on the International Space Station age just a little more slowly than people on Earth. Travelers moving at high speeds or near intense gravitational fields would age differently than those who remain behind. This leads to one of the most famous thought experiments in physics, the twin paradox. Imagine two twins. One boards a spaceship and travels near the speed of light, then returns. The other stays on Earth. When they reunite, the traveling twin is younger. Time itself has passed more slowly for them. This is not magic. It is a consequence of how space and time behave. But these ideas do more than change our understanding of clocks and aging. They reshape our view of causality, of history, of what it means for events to occur. In Einstein's universe, time is not a universal now moving forward. Instead, it is part of a four-dimensional fabric called spacetime. Every event, from the birth of a star to a whispered conversation, exists as a point in this fabric. The motion of objects through space affects their motion through time, and vice versa. Light, which always moves at the same speed, defines the boundaries of causality. Nothing can move faster than light, not even information. This sets limits on what can influence what. The region of the universe from which we can receive signals, our observable universe, is defined by the distance light has traveled since the beginning. Beyond that, there may be more. Galaxies, structures, perhaps even other universes. But they are forever unreachable. Not because they are hidden, but because their light has not yet had time to arrive. Even within the observable universe, different places experience time differently. Stars at the edge of a galaxy age differently than those at the center. Particles moving at near light speed live longer than their counterparts at rest. The cosmos does not tick to a single clock. It is a symphony of rhythms woven together by motion and gravity. And yet, despite all this relativity, there is one direction in which time always moves: forward. This is known as the arrow of time, the asymmetry between past and future. We remember the past but not the future. We see eggs break, never unbreak. Stars are born, they live, and then they die, not the other way around. This arrow of time is deeply linked to entropy, the measure of disorder in a system. According to the second law of thermodynamics, entropy tends to increase. Order becomes disorder. Heat flows from hot to cold. Systems become more random. And as entropy increases, time moves forward. The universe began in a state of astonishing order, low entropy. Over time, stars formed, burned, and scattered their ashes. Galaxies collided. Black holes emerged. Complexity gave way to dissolution. And through it all, entropy increased. This connection between entropy and time remains one of the deepest mysteries in physics. Why did the universe begin in such a low entropy state? What determined the direction of time's arrow? And could it ever reverse? Some theories suggest that under certain extreme conditions, such as at the Big Bang or perhaps the end of the universe, the arrow of time might flip. But no one knows for sure. What we do know is that, in our experience, time moves in one direction. Memory, cause and effect, life itself, all flow from past to future. And so we find ourselves in a universe where time is not a steady beat, but a flexible, relative dimension, one that curves, stretches, and dances with gravity and speed. It is not just something we move through, it is something we shape and are shaped by. Time governs the unfolding of stars, the merging of galaxies, the rise and fall of civilizations. And in the quiet ticking of cosmic clocks, we find both humility and wonder. That in the immensity of space, there is a rhythm, not uniform, not absolute, but real. And it is within that rhythm that we live. Chapter 7: Galaxies in the Dark. Structure, spin, and silent motion. From a distance, a galaxy appears serene. A spiral of stars, glowing faintly against the deep black of space. But inside, it is anything but still. Stars orbit, gas flows, dust clouds collapse into new suns. Entire solar systems move in great sweeping arcs, drawn by gravity into a dance that has lasted for billions of years. A galaxy is not a simple thing. It is a vast, layered structure, held together by forces both visible and hidden. Our own Milky Way is one such galaxy. A flat, rotating disk made up of hundreds of billions of stars, planets, and clouds, all circling a mysterious center. There are many types of galaxies. Spirals, like our own, are shaped like pinwheels, with arms that twist outward from a dense, central bulge. Ellipticals are rounder, older, and often contain less gas. Irregular galaxies defy easy classification often distorted by gravitational encounters with others. Some are dwarfs, small and faint. Others stretch for hundreds of thousands of light years. But no matter the shape, all galaxies are held together by gravity, and it is gravity that reveals one of the most enduring mysteries in modern science. In the 1970s, astronomer Vera Rubin studied how stars move within spiral galaxies. What she found defied expectation. Based on the visible mass of a galaxy, the stars and gas we can detect, stars near the edges should move more slowly than those near the center, much like planets in our solar system. But they did not. Instead, stars far from the galactic center moved just as quickly as those closer in. The rotation curves of galaxies were flat, not falling. Something unseen was providing extra gravity, holding the galaxy together. That something became known as dark matter. Dark matter does not emit or absorb light. It does not reflect, glow, or interact with electromagnetic radiation. We cannot see it directly, but its presence is undeniable. It exerts gravitational pull. It shapes galaxies. It affects how the universe expands. In fact, dark matter makes up most of the mass in the universe, far more than all the stars, gas, and dust combined. Without it, galaxies would fly apart. Without it, large-scale cosmic structure, the cosmic web of filaments and voids, could not have formed as we observe it today. And yet, we still do not know what dark matter is. Many believe it is made of particles unlike anything found in the standard model of particle physics, perhaps weakly interacting massive particles, or WIMPs. Others suggest axions, or even entire classes of particles not yet discovered. There are theories of modified gravity, of extra dimensions, of hidden sectors in physics. We are searching. Experiments deep underground look for tiny flashes that might signal a dark matter particle passing through. Telescopes scan the skies for evidence in the way galaxies bend light, gravitational lensing caused by invisible mass. But for now, dark matter remains a silent companion. It does not burn, it does not shine, but it holds everything together. Beyond this invisible scaffold, galaxies move through space not at random, but as part of larger structures. They gather into clusters and superclusters, immense regions where hundreds or thousands of galaxies orbit a common center of mass. Between these clusters are great voids, nearly empty regions spanning tens of millions of light years. This large-scale structure is sometimes called the cosmic web, a vast network of matter and emptiness stretching across the universe. Filaments of galaxies extend like tendrils, forming intersections where the largest clusters reside. These patterns were seeded by tiny fluctuations in the early universe, amplified over billions of years by gravity and dark matter. And still, galaxies themselves are in motion. Our Milky Way, along with the neighboring Andromeda galaxy and many smaller companions, is part of the Local Group, a gravitationally bound collection of galaxies. Together, this group is moving toward a larger structure known as the Virgo cluster. And beyond that, all are being drawn toward an even more massive region called the Great Attractor, a gravitational anomaly so massive that it influences the motion of galaxies hundreds of millions of light years away. The cosmos is not static. It is drifting, spiraling, collapsing, and expanding all at once. Within galaxies, stars orbit the center. Within clusters, galaxies orbit one another. Within the universe, everything stretches outward, pulled by dark energy, shaped by dark matter, glowing faintly in the dark. Back home in the Milky Way, our own solar system orbits the galactic center at incredible speed, completing one circuit every 230 million years or so. Since Earth formed, we've made only about 20 such journeys. Between the stars, interstellar gas and dust swirl, forming new generations of stars and planets. In some places, massive black holes spin, feeding on matter, emitting energy in invisible jets. In others, ancient stars fade slowly, untouched for eons. To look at a galaxy is to see both past and future. The light we see from the most distant galaxies began its journey billions of years ago. It tells us what they looked like when the universe was young. And yet, by understanding the physics that shapes them, we can also glimpse what they may become. In every galaxy, there is silence, but it is not empty silence. It is filled with movement, balance, tension, and transformation. The universe is not a random scattering of stars. It is a structure, vast, ordered, and darkly beautiful. And in the hearts of galaxies, surrounded by mysteries still unsolved, we find the rhythms that bind the cosmos together. Chapter 8: Signals Across the Void. Light, waves, and the language of the cosmos. The universe does not speak in words. It does not write in ink or chisel its thoughts into stone. Instead, it communicates through signals, through light, particles, and vibrations in space. These messages travel across the darkness, from star to planet, from galaxy to galaxy, and if we are quiet enough, we can learn to listen. For most of human history, the only signals we received from the cosmos were visible light. The stars, the sun, the planets, all gave their secrets through color and motion. But light is more than brightness. It carries information in its spectrum, in its shifts and changes, in its timing. Light travels in waves, but it is also made of particles, photons, each carrying energy. The shorter the wavelength, the higher the energy. At one end of the spectrum are radio waves, gentle and long. At the other end are gamma rays, with wavelengths smaller than the nucleus of an atom. In between lie microwaves, infrared, visible light, ultraviolet, and X-rays, each one a different voice of the cosmos. And each tells a different story. Radio waves, for example, come from cold gas between stars, from distant quasars, from the afterglow of the Big Bang itself. With radio telescopes, We can map the invisible structure of galaxies, detect pulsars, spinning neutron stars that emit precise, regular signals, and search for patterns that might hint at intelligent life. Infrared light, with its gentle warmth, reveals the hidden. It can pass through dust clouds that block visible light, allowing us to see into star-forming regions. It can trace the heat of distant planets, the birthplaces of new solar systems, and even the glow of ancient galaxies at the edge of the observable universe. X-rays and gamma rays, meanwhile, come from violence, from black holes devouring matter, from neutron stars colliding, from supernovae blasting themselves apart. These high-energy messengers speak of extremes, of gravity at its most intense, of magnetic fields twisted beyond comprehension, of temperatures that defy imagining. But light is not the only way the universe sends information. There are neutrinos, ghostly particles that pass through almost everything, born in nuclear reactions in stars and supernovae. Trillions of them pass through your body every second, unnoticed. Detecting them is difficult, but when we do, they offer a glimpse inside processes otherwise hidden. There are cosmic rays, high-energy particles, mostly protons, that race through space at nearly the speed of light. Some originate from the sun, others from distant galaxies. Their paths are twisted by magnetic fields, their origins often mysterious, but they too carry energy and stories from places we cannot yet reach. And then there are gravitational waves. Long predicted by Einstein, they were first observed only recently. These waves are ripples in space-time itself, created by massive objects moving violently. Two black holes merging, for example. When detected, they carry a fingerprint of the event that caused them, its mass, its distance, its motion. In 2015, scientists detected such a wave for the first time. It came from two black holes colliding more than 1 billion light-years away. The signal was tiny, smaller than a proton, but unmistakable. A new kind of astronomy was born. With each type of signal, we learn more. Not because one is better than the others, but because together they form a full language. Multi-messenger astronomy, the combination of light, particles, and waves, allows us to study events from many angles, like hearing both the words and the music of a story. Even silence can be a message. The absence of expected signals can reveal a great deal. If we look where a star once was and find only darkness, it may have collapsed into a black hole. If we search for gamma rays from a supernova and find none, it may have failed to explode. The universe speaks in what it sends and in what it withholds. And as our instruments grow more sensitive, we can listen more closely. Space telescopes orbit Earth, free from atmospheric distortion. Ground-based observatories spread across continents, synchronized by atomic clocks. Neutrino detectors sit deep in ice or water, shielded from background noise. Gravitational wave detectors use lasers and mirrors, waiting for the faintest whisper of movement in the fabric of reality. But there is another signal we have long wondered about, one we have not yet heard. Is someone else speaking? For decades, we have scanned the skies for signs of extraterrestrial intelligence, repeating patterns, unusual pulses, narrow band transmissions. The famous WOW signal, recorded in the 1970s, was a strong candidate, but it never repeated. To this day, no confirmed signal from another civilization has reached us. Still, the search continues. We send signals of our own, radio waves leaking from television broadcasts, spacecraft bearing plaques and golden records, messages encoded in binary and mathematics. Whether they will ever be received is unknown, but in sending them, we acknowledge that we are listeners, and that perhaps someday we might also be heard. In the end, the universe is not silent. It is alive with information, carried across the void by waves and particles, flashes and pulses. Some signals take seconds to reach us, others take billions of years. Some arrive easily, others are buried in noise. But all of them are threads, connecting past to present, star to star, mystery to meaning. And in every signal, there is a reminder that we are not alone in the dark. We are part of a universe that speaks, not in one voice, but in many. And to listen is to participate, to be part of the story, unfolding one message at a time. Chapter 9: Echoes and Shadows, the Cosmic Microwave Background. There is a quiet hum that fills all of space, a whisper from the very beginning. It does not come from stars or galaxies. It does not flicker or flash. Instead, it surrounds us evenly, a cool, faint glow that reaches Earth from every direction. This is the Cosmic Microwave Background, or CMB, the oldest light in the universe. But it is more than light. It is a memory. To understand this faint echo, we must return to the early universe. Not long after the Big Bang, when everything was hot, dense, and opaque. For hundreds of thousands of years, matter and energy were locked together in a blinding plasma. Photons, particles of light, could not travel freely. They bounced constantly, scattering off charged particles like electrons and protons. The universe during this time was glowing, but that glow was trapped. Then, after nearly 400,000 years, the universe cooled enough for something remarkable to happen. Electrons joined with protons to form neutral atoms. This moment, known as recombination, allowed light to move freely for the first time. Space became transparent, and that first light, released at the dawn of clarity, has been traveling ever since. Today, we detect it not as visible light, but as microwaves, stretched over billions of years by the expansion of the universe. It is incredibly uniform, just a few degrees above absolute zero. But it is not perfectly smooth. There are tiny fluctuations, differences in temperature and density, smaller than 1 part in 100,000. These slight variations hold profound meaning. They are the earliest imprints of structure, the seeds of all future galaxies, stars, and planets. Where the CMB is just a little warmer, matter was slightly denser. Over time, gravity amplified these tiny differences, pulling matter together, forming the cosmic web. In the 1960s, this background radiation was discovered by accident. 2 radio astronomers, Arno Penzias and Robert Wilson, were trying to eliminate noise from their antenna, but the signal would not go away. It came from everywhere, at the same strength, day and night. They had stumbled upon the afterglow of creation. Since then, the CMB has become one of the most powerful tools in cosmology. Satellites like COBE, WMAP, and Planck have mapped it in exquisite detail, revealing the shape, age, and contents of the universe. By analyzing the patterns in this ancient light, scientists have determined the universe's geometry, the proportions of dark matter and dark energy, and the timeline of its expansion. In a very real way, the CMB is our baby picture of the cosmos. It shows us the universe as it was when it was only a few 100,000 years old, long before the first stars lit up, long before galaxies spun into shape. And it reminds us that the universe was not created perfect and smooth, but slightly flawed. And it is within those flaws that everything we know was born. There are also shadows in the CMB, subtle dips in temperature caused by massive clusters of galaxies lying between us and that ancient light. These Sunyaev-Zeldovich effects, as they're called, allow astronomers to detect massive structures even when they cannot be seen directly. It's as if the CMB casts shadows across time. And there may be more hidden within this background. Some scientists search for patterns in the CMB that might hint at cosmic inflation, a period of rapid expansion in the universe's first moments. Others look for signs of gravitational waves imprinted on the background, echoes from the earliest tremors in spacetime. The CMB may even hold clues to physics beyond the known, signs of extra dimensions or imprints from a multiverse. These ideas remain speculative, but they remind us that the faint microwave glow is more than a curiosity. It is a frontier. Even its silence is meaningful. The near uniformity of the CMB tells us that the early universe was remarkably well mixed. It suggests that, even before recombination, something connected distant regions, perhaps a brief but violent expansion in the earliest fractions of a second, stretching quantum fluctuations across the cosmos. And so, in every direction we look, we see a message, not written in ink, but in temperature, frequency, and pattern. It is the oldest light, and yet it continues to speak. It tells us that the universe had a beginning, that it evolved. That structure emerged not from symmetry, but from imbalance. That everything we see today, from galaxies to thoughts, has its roots in this gentle flicker of ancient heat. The CMB is always there. It passes through us. It fills the sky. It whispers of the time when the universe first revealed itself. And when we listen closely, we hear more than echoes. We hear the quiet truth that everything, every star, every molecule, every story began with this light, stretched thin by time, still moving, still present. Chapter 10. The Universe Within. Consciousness, observation, and the final question. In the vastness of the universe, among galaxies and black holes, fields and forces, there is one phenomenon unlike any other. It is not made of atoms or light. It does not stretch across space. And yet, it may be the most mysterious force we know. It is consciousness. We often study the universe as if from the outside, as observers gazing into a cosmic theater. But no matter how far we look, no matter how deep we reach, there is one thing we cannot escape. Ourselves, our perception, our awareness, our questions. The mind that asks is also part of the system. In physics, this idea becomes more than philosophy. It becomes part of the equation. Consider quantum mechanics, our most accurate theory of the very small. It describes particles not as definite things, but as probabilities, as waves of potential outcomes. An electron, for instance, does not have a single location. It exists as a cloud of possibilities. Only when we measure it, when we look, does it appear in a specific place. This strange feature is called wave function collapse, and while it is well tested and deeply successful, it raises a troubling question. What does it mean to observe something? Must there be a conscious observer? Or is any interaction with the environment enough? This question is not settled. Some interpretations, like the Copenhagen model, suggest that observation causes the collapse, though they leave observation vaguely defined. Others, like the many worlds interpretation, avoid collapse altogether, proposing instead that all outcomes happen, each in its own branching universe. Still others point to decoherence, where the environment itself plays the role of measurer. But wherever one lands, the role of observation, of measurement, remains central, and that leads us back to consciousness. What is it? A pattern of neural activity, a byproduct of biology, an emergent phenomenon from complexity, or something more fundamental, a property woven into the fabric of the cosmos itself? Neuroscience can map brain states. It can track impulses and chemical flows, but it cannot yet explain the simple fact that we experience, that we feel, that we are aware. And so, amid equations and telescopes, we find ourselves confronting one of the deepest mysteries. What is the relationship between mind and matter? Some scientists and philosophers argue that consciousness arises from complexity, that when enough information flows through a system, a kind of awareness emerges. Others suggest that consciousness is not something the brain produces, but something it tunes into, like a radio dialed to a specific frequency of reality. Still others wonder if consciousness is fundamental, not a product of the universe, but part of its foundation, like space and time. This is not idle speculation. The very act of asking questions, of forming ideas, of doing science, depends on the presence of a conscious mind. Without it, the equations remain unspoken. The stars shine, but no one sees. The signals travel, but no one listens. Consciousness is the medium through which meaning arises. And this brings us to a quiet but powerful realization. The universe does not merely exist, it is known. Even the most distant galaxy, seen through the lens of a telescope, becomes part of our awareness. Its light, which traveled for billions of years, ends its journey not in silence, but in understanding. The moment it enters our perception, it changes. It becomes part of our story. And perhaps this awareness is not separate from the universe, but an expression of it, as natural as gravity, as real as time. Some traditions, both philosophical and spiritual, have long held that mind and cosmos are not distinct, that the separation between self and universe is an illusion, that to know is to participate, that to observe is to create. Modern physics sometimes echoes these ancient ideas. The participatory universe, suggested by physicist John Archibald Wheeler, proposes that reality itself may be shaped by acts of observation, that without measurement, the universe remains in a state of potential, and that through conscious beings, the cosmos becomes actual. This is not to say that reality depends on us. The universe existed long before human eyes opened, but it may be that reality, in its deepest sense, is not fully defined until it is experienced. And so, from stardust, we rise, not only to look at the stars, but to wonder what it means to look. We are made of the same particles as the stars, the same hydrogen that burned in ancient suns, the same carbon born in supernovae. Our thoughts are patterns of energy shaped by biology, but echoing the rhythms of the cosmos. In us, the universe gains the ability to ask about itself. This raises a final, profound question. Why? Why is there something rather than nothing? Why does the universe have laws at all? Why are those laws intelligible to the human mind? Some suggest that it is all chance, that given enough time and space, even conscious beings must arise somewhere. Others see purpose, design, or meaning woven into the structure of reality. Still others believe the question itself may be flawed, that the universe simply is without why. We do not have the answer. Perhaps we never will. But we do know this. The universe has grown stars, planets, life and mind. It has unfolded from simplicity to complexity, from chaos to order and back again. And in that unfolding, it has given rise to something that can imagine, reflect, and seek. Even now, as we drift through space on a small blue planet, we look outward and inward at once. We build machines to catch the light of ancient galaxies, and we close our eyes to wonder what it means to dream. We trace gravity
through equations and feel its pull in the weight of our lives. We study black holes and ask what lies beyond memory, beyond death, beyond understanding.
The universe has no obligation to make sense, and yet it does.
Not completely, not easily, but enough for us to build ships of thought and sail them into the dark, guided by starlight and questions.
We may never reach the edge of it. We may never find all the answers. But we are part of the journey. We are, in some small and fragile way, the universe becoming aware. And perhaps that is enough.
Not to conquer mystery, but to meet it. Not to solve the final equation, but to hear the music it plays. Not to own the stars, but to sit beneath them, quietly, thoughtfully, and feel them in our bones.
The universe is immense, but the mind is wide enough to hold wonder. And as long as we ask, as long as we listen, the conversation continues.